know. Wow. Okay. Hey, remember how yesterday we were talking about this thing called delta H? What's delta H? Enthalpy. In just like layman's terms, what's enthalpy?
Bonds broken.
Sure, you could calculate it using that equation, but like, what is it? What is enthalpy?
Now the energy needed to do a reaction.
Yeah, it's an energy absorbed or released by a reaction. What's an easy word for that besides energy? What kind of energy? Heat. It's heat, right? This is heat of a reaction. And what did we say was favorable? Like when a reaction is what, it's more likely to occur spontaneously? Exothermic, right? So we said like, hey, if it's exothermic, that's going to be like favorable, like a negative delta H. And if it's endothermic, it'll be like less favorable. It's not impossible though, right? Positive delta H. Now notice I didn't say this is a rule, right? I was like, hey, favorable, less favorable. Why? Enthalpy is not the only thing that matters. What's the other thing that matters? Entropy, delta S. Okay, delta S, entropy. What is entropy? Good. We're going to say disorganization. It's the disorder or messiness of a reaction or a substance, right? But we're talking about deltas, so we're talking about changes for reactions. Okay, what did we say was favorable? Messier is favorable. So a positive delta S, more disorder, we said was favorable, right? And a negative delta S, more order, less favorable. So we can see here, you guys, that it could be very possible, right? That we have something that's favorable in terms of enthalpy, like a negative delta H, right? But something that's not favorable in terms of entropy, a negative delta S. How do we know if this reaction is going to be spontaneous or not? We got to look at the relationship between the two, all right? And the guy that figured that out was the name of Gibbs, all right? And he came up with a new variable called Gibbs free energy. All right. Gibbs free energy looks at the relationship between, whoa, I just put 3 E's. I just put 3 E's in between. Between enthalpy, entropy, and temperature. Okay, so the temperature that something is happening at, temperature, also matters. To determine spontaneity. So like, if a reaction is spontaneous, like in the forward direction or in the reverse direction, like whichever direction it's spontaneous in, it means it's going to happen on its own and that it can do work. Like if a reaction has energy to give to the universe, it means that we can use that reaction to do work. Like the gases expand and they push a piston, or it creates a bunch of heat and that heat can boil some water. Like it can do work. And that's actually what this free energy is, all right? It is a measure of energy available to do work, okay? So what we're going for here is an equation. And listen, all of these equations can be derived. And if you're curious and you want to go read chapter 19 and see all the derivations, great. Today, I'm just going to ask you to take my word for it that these are the equations. You don't need to memorize them. They will be on your AP equation sheet, okay? So The equation that relates these three variables, this is one of my favorite equations. I don't know why, it's just so nice and simple. Delta G is equal to delta H minus T delta S. Since endo is less favorable, we put more energy in. Okay, so I think I'm going to answer this question. Isabella asked me a question in the chat. Isabella, I think I'm going to answer this question as we go. All right. And if this doesn't sit better with you when we're done, ask it again. Okay. So I'll come back to it. Okay. All right. So delta G, you guys, the delta G is your free energy. That's Gibbs up here. This guy, delta G, free energy. Delta H is obviously your enthalpy. And delta S is your entropy. Now, when we were working with these values yesterday, you guys, enthalpies are typically in kilojoules and entropies are typically in joules per Kelvin. So if you're going to use this equation, you've got to make sure you convert. Like you got to make sure, obviously, that your temperature is in Kelvin. And you'll probably need to convert your entropy from joules to kilojoules, right? So that you can get a free energy in kilojoules. This is the energy available for that reaction to do work. So let's take a look just qualitatively, like without any numbers. Let's just take a look at this whole favorable, not favorable thing and see how it relates to free energy. And this maybe will answer Isabella's question. Let's say I have a reaction that is exothermic, right? So that's going to give me a negative delta H, all right? So imagine you have a negative sign here because this is exothermic, which is favorable. Let's say we have a positive delta S over here, more disorder, which is also favorable, right? If I have a negative here and I'm subtracting a positive, right? Like let's just look at the math here. I'm subtracting temperature times a positive value. What am I going to get for a delta G? Like is my delta G going to be positive or negative here? A negative minus a positive is always what? Negative, because this is the same thing as adding a negative, right? Do you see how this delta G is always going to be negative? If you get a negative delta G, that means the reaction is spontaneous. And that makes sense, right? A negative delta G being spontaneous makes sense because, look, exothermic, that's favorable. More disorder, that's favorable. If I have two favorable conditions, nothing's going to prevent that reaction from happening spontaneously, right? It will always be spontaneous, okay? Let's add a note up here to our definition on delta G here. If you have a negative delta G, the reaction is spontaneous in the forward direction. All right, let's look at an alternate scenario here. All right, so instead of purple, this time I'll use green. All right, what would happen if my delta H was positive? Positive value here, meaning endothermic. And a negative delta S here, negative delta S, less disorder. not favorable. So look, not favorable, not favorable. Let's just look qualitatively at the math here. If I'm subtracting temperature, if I have a positive value and I subtract a negative value, what's my answer guaranteed to be? Positive, right? I'm going to have a positive value here. This is going to be not spontaneous, always. And that makes sense, right? Because this is not favorable, and this is not favorable, okay? So if you get a positive value for delta G, that reaction is not spontaneous in the forward direction. But it would be spontaneous in the reverse direction, okay? So let's add that note, shall we? Up at the top next to our definition for delta G. I've now proved to you using this equation, the negative delta G is spontaneous in the forward direction. A positive delta G, the reaction is not spontaneous in the forward direction, but is spontaneous in reverse. It's just telling you which direction this reaction is going to proceed. Kind of like equilibrium, right? Remember when Q is greater than K, we're like, oh, the reaction's going to go this way or that way. If you get a delta G that is equal to 0, so we've been talking about positive delta G's, we've been talking about negative delta G's. If you get a free energy that's equal to 0, it's going forward and reverse at equal rates, right? It's not spontaneous in one direction or the other predominantly. It's like nothing is happening. It's like nothing is changing. It's like you're at equilibrium. There's no work left to be done.
Are you at equilibrium?
Yes, you are at equilibrium. Okay? You can think about it like a ball rolling down a hill, right? Like a ball will spontaneously roll down a hill and it'll rock back and forth and rock back and forth and it'll come to settle at the bottom of the valley, right? And at the bottom of that valley, that rock is no longer doing any more work. There's no more free energy available. Like it's no longer moving and it no longer has any potential energy. It's sitting down there at the bottom. It is at equilibrium, okay? Now, back to my little color-coded diagram here. Do you guys see how I just looked at two scenarios? I looked at a scenario where like both things were favorable or both things were not favorable. What's left to talk about? What scenario is there still to investigate? One of each. What if one thing is favorable and the other thing is not? And maybe this will answer the rest of your question, Isabella. Instead of just continuing downward, I'm going to go to the right and let's write the equation again, you guys, so that we can work underneath it, just for logic. So delta G is equal to delta H minus T delta S. All right, this is my equation, my little logic puzzle. All right, let's do blue. What if I have a negative delta H, okay, which is exo and favorable? And you're like, okay, cool. But what if I have a negative delta S, which is less disorder or more order? That is not favorable, right? So I have one thing that's favorable and one thing that's not favorable. Sometimes this reaction is going to be spontaneous and sometimes it's not. What's it going to depend on? What's the third factor in here, you guys? Temperature. It's going to depend on temperature. So let's take a look. Tell me, so you just got to use a little bit of math logic here. Tell me when are we going to get a negative value here? Like, when are we going to get spontaneous? Like, what kind of temperature would I need to get a negative value out here? Do I need a big temperature or a small temperature for this to be negative? So subtracting a negative is the same as like adding a positive. So for this to be negative, does this temperature value need to be high or low? Low. It needs to be low. You need a small value. Okay. This will be spontaneous at low temperatures. Right? Because if this is plus a positive, we need this value to be bigger than the product of those values. Okay, so this will be spontaneous at low temperatures and not spontaneous at high temperatures. So I think, Isabella, you were asking, like, well, what could we do to get something that has these competing forces to be spontaneous? You could mess with temperature. Does that sort of answer your question? I can't see you, Isabella, so if you're nodding, hopefully you're nodding. All right, let's take a look at what would happen. Thank you. If the opposite thing were going on, right? I need one more color. We'll do orange. All right, let's say we have a positive delta H, which is endothermic and not favorable. The AP exam loves these qualitative questions about this equation. Like, I would almost bet my life that there will be one of these on the AP exam. All right, like where they give you signs of H and S and they ask you to predict about delta G. So this is not favorable. And let's say delta S is positive, which is favorable. More disorder, which is favorable, right? Oh no. All right, so let's think about, just like we did before, what is gonna make this reaction spontaneous? So minus temperature. When are we gonna get a negative value for delta G here? Like, when is this reaction going to be spontaneous? What can we do to override the fact that this is endothermic, you know, which is not great for us in terms of spontaneity? So how do I get a negative value out here? High temperature or low temperature? High. Okay, so this will be spontaneous at high temperatures. Do not memorize these 4 sequences, right? Just like use your brain and your logic and like plug in pluses and minuses and stuff. And so this will be not spontaneous at low temperatures. And some of you might be like, well, like what's high and what's low? You know, like what qualifies? You could always plug in a 0 for delta G and solve for temperature, right? If you plug in a 0 for delta G, that's your dividing line between positive or negative, right? Solve for temperature. You're above that temperature, you're below that temperature, you can figure out spontaneous or not, okay? So you can actually calculate what that temperature is by plugging in a 0 for delta G, okay? All right, let's do one more thing and then we'll do a practice problem. Okay, so this is one way to calculate free energy, is by looking at the enthalpy and the entropy of a reaction. But just like we were able to do for delta H and for delta S, we can also calculate delta G by using standard values, okay? You can get a delta G for a reaction, a standard delta G, by using the G's of formation of the product minus, are we sick of this equation yet? The G's of formation of the reactant. All right, so those are just like standard free energies of formation. We use this exact same formula for delta H of a reaction, we learned yesterday, you can use this exact same formula for the delta S of a reaction. Okay, you can always do the products minus the reactants. Just like delta H, the G's of formation for elements in standard states, that just means like their normal state of matter, are equal to 0. Just like heats of formation for elements in their standard states are equal to 0, okay? The reason why these values of formation, free energy of formation, heat of formation, the reason why these are 0 for elements is because all of these elements were formed during the Big Bang. We're not forming any new elements. That's why, like, when we read the Mighty Atom chapter way back in honors in CP Chem, you remember reading in there that like there are atoms in your body that could have been in a dinosaur, right? There are atoms in your body that very well could have been in Einstein or Marie Curie, right? Like these atoms have been here forever, okay? These elements have been here forever and they're just getting recycled. So that's why they have no free energy of formation and no heat of formation. The S naught values, okay? The S naught for elements is not equal to 0. The entropy, the disorder. The only time there's 0 disorder is when you're a pure substance at 0 Kelvin. Remember we learned that? That's the third law. Okay, so the reason why S's are not 0 for elements is because like, even if it's a pure substance, if it's that temperature, it's moving, and that's disorder, that's messiness, okay? All right, now we can do a practice problem. All right, let's write out a reaction. Example problem. All right, the combustion of, hang on, I took a picture of what I wanted to do. Oh, what a disaster. C3H8. C3H8 gas plus 5O2 gas. Yeah? You're going to invent a new element? Go for it. Plus 4H2O. Ah. All right. The delta H for this reaction is negative 2220 kilojoules. All right. Let's just like look at this reaction. What type of reaction is this? It's exothermic. Good. Yeah, it's releasing heat. Is that favorable or not? Yeah, it's favorable. What else about this reaction? What type of a reaction is it besides exothermic? It's a combustion reaction, right? And that makes sense that a combustion reaction would release heat, right? Let's make a qualitative prediction about the sign of delta S. Like I'm not giving you any values yet to calculate entropy change, but let's just like look at the disorder. How many moles of gas do I have on the left? 6. How many moles of gas do I have on the right? 3. This is a liquid. Careful. States of matter, right? So if I have 6 moles of gas on the left and 3 moles of gas on the right, is this becoming more ordered or more disordered? More ordered, right? It's becoming more ordered. I'm making a liquid. Gases are messier, right? So if it's becoming more ordered or less disordered, what sign should I get for delta S? Negative, right? I should get a negative. So check this out, right? I've got a negative delta H. That's favorable, right? I've got a negative delta S. I haven't calculated it yet, but it's negative. That's not favorable. How am I going to figure out if this reaction is spontaneous in the forward direction or not? I'm going to need to calculate delta G. I need delta S And then I need to calculate delta G, okay? So let's calculate delta S first, and then we'll calculate delta G. To calculate delta S, I want you guys to use the delta S of the reaction, the equation from yesterday. The sum of the individual entropies of the products minus the sum of the entropies of the reactants. Okay, this is the equation we're going to use first. And I need to provide you with all of these standard values, right? I need to look them up in the back of the book. I'm just going to write them up above the equation in purple. This one is 269.9. And I know this is just like plugging and chugging, but we're going to tie it all together at the end. 205.0. Remember, elements are not zero. Look, even though that's an element in its standard state, it's still got an entropy. And the carbon dioxide is 213.6. And the water is 69.91. Do you guys see how the gases have more entropy than the liquid? Like, just look at the numerical values. See how the gases are messier than the liquid is, right? Makes sense. All right, so plug and chug, please. Use these purple values and the moles from your balanced chemical equation. Give me like an actual numerical value here for this delta S that we predicted would be negative. Hopefully it comes out negative. Plug and chug. What?
Nothing.
Okay. Are you having fun yet, Julia? I know.
What you doing?
She's grading my honors lab.
Bruh.
Bruh. You ready to do some grading, Anthony?
Miss Brad,
Anthony's gonna give everything.
neither of
a grade.
us trust me with doing that.
I do not want Anthony getting my lab.
Anthony can follow instructions.
I'm grading labs, everyone's getting hundos.
All right.
Unless
Yeah.
they like do some stupid shit like forget the indicator, you know what I'm
No, just like randomly subtract like 5 points from one part and then
Just
just
for
like
the hell
write
of
like
it.
a stupid reason, be like, that's not, I don't know.
saying? Your handwriting sucks. Minus 10.
Like all wrong.
Yeah.
Redo.
Show your work minus 15. Too bad.
Forgot.
Yeah, we're supposed to be calculating.
I'm waiting on Kevin to give me the answer.
I'm waiting on Kevin to give me the answer.
Negative what?
I'm not showing out my work. So if you get it wrong,
0.5.
I'm not telling you why.
Oh,
Isn't that good teaching?
kilojoules.
No, not kilojoules. Joules. Joules. Joules.
So
Joules.
it's just 3.745 kilojoules.
I got negative 374.5 joules per Kelvin. Did anybody else get that?
Okay.
Yeah.
Okay. Now, the moles cancel, right? Because when you're multiplying by moles of each substance, right? When I multiply by 5 moles of O2 or 1 mole of the C3H8, right? Moles cancel. This is the entropy. Is it negative like I predicted? Yes. Okay, good. So now you guys, please use your delta G equals delta H minus T delta S equation. Use this equation to tell me whether or not this reaction is going to be spontaneous. All right. Now, careful. Your delta H is in kilojoules. Your delta S is in joules, right? And your temperature needs to be in Kelvin. Oh, what's the temperature this reaction is taking place at? I think it's 298. Yeah. At 298 Kelvin, tell me if this reaction is going to be spontaneous or not, because we know it's going to depend on temperature. So I have one thing that's favorable and one thing that's not favorable, so the temperature is gonna matter. Put everything in the right units, plug and chug, and tell me if this reaction is gonna be spontaneous.
Does that matter?
Jordan?
I'm sorry, I don't know these. I think it's 1,000, right?
There are 1,000 joules per
Okay.
joule.
That's what I thought. Matters just
I
said it's
still
trying
get
to
tripped
be
up on.
so
Nope, it doesn't matter.
No, like
weird.
meters and kilometers, I
I
still
literally
don't
went
know.
gross.
No, I know that one, but I don't know centimeters.
Yeah.
Well, like 1,000 meters is a kilometer, but centimeters is a meter.
100 centimeters in a meter.
No,
Centis are smaller.
I don't know any of that.
I
Would
I've got
you
moment.
want us to convert it
no,
from like
like
kilojoules
Okay,
to joules?
So Avery asked the same question. Does it matter if we go joules to kilojoules, blah, blah, blah? The delta G's make more sense in kilojoules. Okay, so I would change my joules to kilojoules because the delta G values tend to make more sense in kilojoules.
whoa.
No, I thought we were already in. Perfect.
Dude,
Heat is in
there's so much-
kilojoules.
Okay.
Your heat is fine. You need to convert your delta S.
Kelvin is over Kelvin. So you got a Kelvin in the Newton and a Kelvin in the Denami.
That's right, they do. The Denami, the Numi and the Denami. I'm gonna call them that now.
I thought that
Newton and the Denami. That's
like
fine.
in the
I just
equation,
thought-
like
So what do you got for
entropy and
uh, entropy and
what is it, joules over?
kilojoules? Hold up, don't move.
It all looks the same.
Honest to God. Sometimes I just like wish that like people who were not teachers could just like come and sit in here for a day. Just to
I can
see.
sit in.
Just to be like, wow, you're a saint.
We should watch Titanic.
What?
I've never sat through and watched Titanic. I get too bored. It's really fun. I get so bored, I can't watch the whole thing. Isn't that incredible? Yeah.
I've never watched it.
I've watched like the ending and the beginning. I can't watch it. It's like I literally
Does it
can't.
worth like the time?
It's not worth 3 hours of my life. It's not like this AP test that we're gonna take. It's not worth 3 hours of my
She
life.
was in and out a lot. So.
There's some drama going on in the family.
All right, ready?
Yeah.
My dad used all the data and then he blamed it on my mother. And now,
Your mother?
yeah, and now my mom's like turning data off and it's $15 for every extra.
Phoebe, look.
When you-
Phoebe,
what's your thing?
I'm gonna convert my joules to kilojoules. Negative point
Right?
374.
I thought we left it as.
So funny.
What? Oh, I did this wrong. I got it. Really not.
Okay, look. You guys, the delta S is in joules per Kelvin. Honest to God, are we in 3rd grade? This is in kilojoules, right? Are kilojoules and joules gonna be able to subtract? No, they have to be in the same unit. All right, the Kelvin is gonna get taken care of because you got a Kelvin in the Numi and a Kelvin in the Denami,
Nice.
and they're gonna cancel. All right, I think it makes more sense to be in kilojoules. So when I get a delta G for this reaction, what did I get? What did you guys get?
Kevin got negative
Kevin got
2,108.41.
negative 2108. We'll just go with this. Great. What does this mean?
It's spontaneous.
Spontaneous. It is a spontaneous reaction in the forward direction. Got it? Cool. Oh gosh, there's a lot of erasing happening. Questions? All right, now, last thing we have to do is we have to tie this back to equilibrium a little bit more, okay? So we've got heat. Heat can be released or absorbed. Easier for reactions to release heat. Well, not easier, it's just like more natural, more spontaneous, more lends itself towards spontaneity. Reactions can turn into messier stuff or they can become more organized, right? And it's the balance of these two things that determines whether or not this thing goes in that direction, or goes in that direction, or goes in both directions at the same rate. Got it? All right, we're scrolling down. Yeah, I got room. Okay, here we go. Free energy and equilibrium. Let's relate these things. Free energy and equilibrium. Don't throw things at each other,
I'm
children.
not. I promise. You wouldn't.
I literally just saw you. Okay. So, I like the analogy, and I know I've said this a couple times now, of a ball rolling down into a valley. All right, so imagine this is our valley. If I have a ball or a rock or a boulder or whatever up here in the valley, which way is it spontaneously going to roll? It's going to roll this way. It's going to roll forward. If this is the ball rolling forward, right? If this is the reaction going spontaneously in the forward direction, we would have a Q value that is less than K. This is not new information. Do you guys remember this from equilibrium? If you have a K value and you have a Q that's less than K, the reaction is spontaneously going to go forward to get to equilibrium, right? And if you have a Q value that's greater than K, it's going to go in reverse to get to equilibrium. So if I have this reaction that's spontaneous in the forward direction, that means I'm also going to have a negative delta G. Okay, so what I want you to start seeing here is that there is going to be a quantitative relationship between delta G, K, and Q. K being your equilibrium constant, Q being your reaction quotient. These are just like the amounts of the substances that you have and figuring out which way the reaction is going to go to get to equilibrium. What if the ball was starting over here on this side of the mountain? Which way is it spontaneously going to go? That way. This would be like if you had a Q that was greater than K. If the reaction's spontaneous in the reverse direction, sorry for you guys, reverse direction, what kind of delta G am I going to have? Positive. Okay. Now, what if the ball is sitting at the bottom of the valley? Can it do any work? Or has it done all its work? It's done all of its work, right? If the ball is sitting down at the bottom of the valley, you're at equilibrium. Your Q is equal to your K value, right? Your delta G, there's no energy left. There's no work left to be done. There's no free energy available. Everything has happened, okay? So, again, this is just like a qualitative thing to help you guys like conceptualize, all right, there's a relationship between spontaneity and equilibrium. Mathematically, what is it? Well, I'm not going to make you derive them. I'm just going to give you 3 equations. Got it? You'll just sort of take my word for it that these are the mathematical relationships so that we don't have to derive everything. Okay, here is the first equation relating free energy to this reaction quotient. Your delta G under any conditions, so notice I didn't put a standard, is equal to your delta G under standard conditions plus R times T natural log of Q. And again, these are all going to be on your equation sheet. All right, so this would be your free energy under any conditions. Any conditions. This is your delta G under standard conditions. And standard, I'll remind you guys from yesterday, standard is 1 atmosphere of pressure for your gases, 1 molar of concentration for your solutions, and 25 degrees Celsius or 298 Kelvin. Okay? Because we're talking energy, this is my energy R, the 8.314 joules per mole Kelvin, not the 0.0821, right? Not the liters atmospheres one, but the energy one. T is obviously temperature in Kelvin, and Q is that reaction quotient, right? Remember that one that tells you if your reaction is going forward or reverse to get to equilibrium. And I'm just going to give you guys all three equations first, and then we'll do practice problems with each of them. It's literally just plugging and chugging. Jordan.
Like the AP test, or like, will we get
Yep, so tomorrow I've scheduled nothing but practice problems in chapter 19. And so we'll have time tomorrow to talk about more about the AP exam, the format for it, the resources that you have, what that equation sheet looks like. You actually have the equation sheet. I gave it to you in your resource section. I think it's on a yellow sheet of paper. Yeah. Okay, so this is the relationship, you guys, between delta G and Q, the reaction quotient, like making a prediction about whether or not we're going to equilibrium or whether we're at equilibrium yet. We can also relate this directly to K, the equilibrium constant itself. Your delta G standard is equal to negative R times T ln of K, the actual equilibrium constant. Okay, equilibrium constant. Same thing, R is your energy R, 8.314 joules per mole Kelvin. And this is your standard condition free energy. Standard condition free energy. And then the last equation, you guys, is actually just a derivation or a solving for K in this equation. Like, this equation is great because if you know how much free energy is available, you can calculate the equilibrium constant, K. Or if you want to know the free energy and you know the equilibrium constant, you can do that too, right? It shows you this relationship between these three variables that I was telling you up here conceptually are related to each other, right? This is just a mathematical relationship between those values. Which way is this reaction going to go spontaneously? So if I want to solve this reaction for K, I need to take the anti-natural log. Remember, it's e to the negative. That's your anti-natural log. E to the negative delta G naught over RT. This would just be like this same equation, but you're solving for K. Reminding you guys that the anti-natural log is this e to the, okay? It's above the natural log function on your calculator. So this is just same equation, rearranged, okay? All right, let us practice with the chapter 19 exercises again, okay?
What's that? G?
E, it's an e to the negative delta G naught over RT. That e is the anti-natural log button on your calculator. So like it's above the natural log. It like undoes your natural log. All right, so I'm gonna stop recording.